Are you stuck up with your real analysis problem in your math class? Are you finding real analysis to be really difficult? Are you not enjoying real analysis? Are you really confused in which way to start real analysis because your professor might assume something? Are you really finding yourself in a confused state while dealing with real analysis? Well, in this video, I'm going to talk all about real analysis, starting from the very concepts, the basic ideas, the practical applications of real analysis, why will you do real analysis, and all the areas which might be cropping in your mind and creating a confusion, and you're not really enjoying what is real analysis actually about. Sit back and enjoy, because this video is going to give you a complete approach into a study methodology and various techniques, methods, and tips which would make your real analysis class beautiful, and you're going to enjoy the real beauty of mathematics once you understand that. To start with, what is real analysis? Now, I know those viewers who are viewing this video, they might be a math major or a physics major where you have already done real analysis, you're doing real analysis, but the basic idea behind this is that what is the real meaning of real analysis and why it is called real? Well, we all know that real analysis deals with calculus. Yeah. So what is that? What is that calculus and real analysis is related to each other? So first of all, what I would like to tell you is that real analysis is a subject which deals with sequence, limits, integration, differentiation, series, convergence, some part of sequence of functions, divergence also. But what I would like to tell you is that we all understand when we did calculus 1, 2, or 3, there are certain definitions, there are certain theorems, there are certain, I would say, ideas which were not rigorous. When I say not rigorous, what I'm trying to mean is that there are certain formulas which are given to us. For example, rules of differentiation, for example, the chain rule, all of this. But remember that these definitions or these formulas were not defined. So first of all is that there should be a rigorous definition of each and every concept. For example, limit. And this rigorous definition of limit, as well as the rigorous definition of continuity, and a rigorous, I would say, definition of differentiation, all these constitute real analysis. So what I can tell is that integration, limits, differentiation, continuity, how we actually understand and find the proofs, that is what real analysis is all about. So what I'm trying to tell is that these are the building blocks. Okay, so suppose we are building a kind of a building, and we are given certain bricks or certain formulas which directly fits in that kind of a building when we are making that building or building up a concept. But try to understand that these concepts or formulas or whatever the things that we do in calculus 1, 2, and in our school or our college days, we really don't know what is the meaning of those definition. How can we prove those formulas? Can we extend the formulas or the rules or definitions up to any dimension? Can we further extend it? What are the intricate details of those functions? So in all, what I can tell you is the calculus that we have read in our school or our college days, now real analysis would further go into the definitions, theorems, and formulas of calculus, and we will really understand what this and how these definitions came. So first of all, what I can tell you is that the general form of the functions and sets and how to prove these properties are being extended to a larger extent. So first, let us understand that all those formulas that we use in calculus, all the concepts, theorems that we use, how we have arrived to that conclusion, what are the proofs, and how we can generalize, just the way we have been talking. If you have seen my lectures on general theory of relativity, I always tell that more we generalize those concepts, the broader it becomes and more easy it becomes for mathematicians and physicists to extend it to different spheres of physical problems. So real analysis actually proves those formulas, extends the concepts of calculus up to any extent. So here on your screen, here is a definition, which is generalizing the concept, so you can quickly read it. Okay, right on your screen. So in order to generalize and prove those properties, as you can understand. So in one sense, you can tell that we are going back to the roots, right? So we are going back to the roots and we are trying to understand why it is so, why it is that, and how we can generalize and extend those concepts so that we can extend into higher dimensions or a further generalization. So in one sense, here again on your screen, this is another a definition of real analysis. This is kind of an intuitive understanding, so I call it calculus is a subset of real analysis. So if you take a calculus, then the superset is the real analysis because it gives birth to calculus. It is the mother. So we are going to understand the mother right now. Another very interesting definition of real analysis is here right on your screen. So we can call it, it is a well-proven framework to support spatial and conceptual ideas that we frequently take for granted. So most important is that those which we take for granted, those which we never ever question, that okay, the formula is, so let us use this formula. So this is where the framework to support spatial and conceptual ideas which are taken for granted, now we are going to understand that. So from this definition, I hope one thing is very clear, that there cannot be any unproven assumptions, right? So real analysis won't have any unproven assumptions, and it would start proving everything right from the point go. I remember, if you have read, I don't know whether you have read it, Bertrand Russell and I think it was E.N. Whitehead, who had a magnum opus called Principia Mathematica, which was later proved to be wrong by Kurt Gödel, the famous Austrian philosopher and mathematician who is known for his incompleteness theorem. So Principia Mathematica actually is something, I would say not equally, but I can tell you this is something like this. So Principia Mathematica actually went down to logic and find out and proved even why 1 plus 1 equals to 2 and why 2 plus 2 equals to 4. So we are going back to the roots. So just like Principia Mathematica, Bertrand Russell and Whitehead proved, going to the basic operation level of arithmetic, we can term real analysis something like that. So first of all, there are rules like transitivity rules, distributive law, commutative law, closure property, associative property. These are taken one by one and they are proved in real analysis. I am trying to give you all those examples so that I can really make you understand what real analysis is all about, so that when you keep on studying, you get the real interest about. So here on your screen, we can say that number one, it is rigorous. Okay. Number two is that it should not have any unproven assumptions. Number four is that we have to define real number axiomatically. We will come to what is axioms and why we want to define real analysis axiomatically. And these are much more theoretical, rigorous, and proof-based mathematical model. Okay, so far so good. So what we have understood, that it deals with the concepts of calculus. We are going to extend the concepts of calculus up to any dimension, and we are going to understand and prove each and every formula, more or less the formulas which we use in reanalysis, and we assume that there are no I would say, there are no unproven assumptions. Everything is proved, everything is quite clear in front of us. Now, the question is that whatever we have been talking for this time, can we prove it in steps? I mean to say, can we give a kind of a hierarchical, methodical way in what real analysis deals? So here on your screen, first of all, it first defines real number axiomatically. Now, I won't tell you right now as we progress with the video Why axiomatically? Let us understand that these are first axioms, Playfair's axioms, or whatever the Euclid's axiom we have. So we are first defining it axiomatically. Okay. The second point which you see on your screen is that we set down the properties which we think define the real number. So then we define the properties of real number. Third, what we do is that we prove these properties, and these properties only, that the real number behave in the way which we have come to understand that regular objects in space behave. So I can repeat, it is to we prove from these properties, the properties that we lay down, and these properties only, that the real number behave in the way in which we have come to understand that real objects in space behave. Fourth point, very important, we build a number system and show obviously it satisfies those properties. So we'll build a system and then we show that it satisfied what we have proven, what we are laying down. Fifth would be, from those foundation we will develop first a set of results about the real number line. We will come later in the further videos where I would be showing you more about mathematics. So from that foundation, we develop first a set of results about the real number line. And lastly, which is quite easy, we move on the results to two-dimensional plane of real number, and eventually we generalize our results into n dimensions. So as you can see on your screen, what I have shown, these are the steps. So first we define the real number axiomatically, then we set down the properties, then we prove these properties from those properties that the objects in space behave. I mean to say the general applications. Then we build a number system. Obviously, we have to build a system. From that foundation, we develop first the results about the real number line, what is the output, and finally we move on to two-dimension, and further we generalize into n dimension. So that is the basically the objective of real analysis, so that we can develop a kind of a formula, a kind of a rule which can be further extended. So I think that this part of the video is clear. What is real analysis? What is the objective behind real analysis? So that part, once it becomes clear, then we can move on to the second other part. So this gives you a kind of a summary in layman's word, what is real analysis all about. Okay, this is a very important, I would say, topic or subject, or the whatever the way we can call, because I have been interacting with a lot of data scientists these days over LinkedIn and in the international community. So obviously the question starts that if data analysis is such a promising career with a lot of remuneration and a lot of international accolades coming across, is real analysis helpful for a person who is pursuing a career in data science? Now, with my experience talking with specialists of real analysis as well as data science, is that this gives you a problem solving ability. Now try to understand that what is data science all about. Data science obviously deals with data, huge amount of data. It can be any amount of data. It can be astronomical data, it can be business data, it can be anything. Now once we start analyzing those data, what we require is huge number of mathematical algorithm and obviously statistics. So what I would like to tell you is that try to understand that this knowledge is just like a pyramid, right? So the base level is a very broad level where we start building the basis, and try to imagine the pyramid mentally, that as we move up the ladder, right at the top, right at the tip, things become much, I would say, much sharper, and things become a little bit narrower. But right at the base, things are very general. So more we move up the pyramid, things become narrower, shallower, until it reaches and culminates to a particular point. So because knowledge is like a pyramid, so we build one on the other. So data science, because it deals with data, because it deals with number, real analysis and the study of real analysis, mathematical models, especially what I would say the analytical power and the problem solving abilities, going to the root of the problem, that actually helps in data science. Now, let us say, for example, I would use one thing which is called a central limit theorem, which you all know. It means distribution of sample which approximates at normal distribution level. So If you take central limit theory, it is very easy to prove, no problem. But until you deal with real analysis, right? Real analysis, I would say analysis part 2, you won't be able to understand what is this central limit theorem is all about. And until you understand the root of that, you won't be able to create new methods and new pedagogies for, I would say, real data science. Central limit theorem as itself is very simple, but until you go and understand, I would say, measure theory, for example, I think it is real analysis 2 measure theory deals with that. Then you will understand, oh wow, what beautiful the sky is, or how beautiful the mathematical model is. So central limit theory is just an example. The statistics deals with convergence, sequence of random variables, and other numbers, statistics. And these will lead to a better data science model. Until and unless you understand the roots, first of all, you won't be able to do great things. I mean to say, you can obviously do data science, you can earn a lot of money, you can set up your career, but you won't be able to do great things until you go back to the roots. That is number one. And the problem solving ability, and most important is that you won't be able to enjoy the mathematics, you won't be able to enjoy real analysis or data science. So these are few which I have gathered talking to few data science across LinkedIn and other universities, that yes, real analysis in a face value not required. You can become any data science without the knowledge of reanalysis. But if you really want to go to the roots and create something great, mathematical models or business models, you need to understand reanalysis. So this section, I think that it has helped you to understand, yes, reanalysis to some extent would be required in order to have a wonderful, great career in data science. Okay, this is very important, and I always encourage my students that before you undergo and study a subject, you should know why you are studying the subject. Now, come on, you are dealing with math major, etc. Your professor assumes certain things, and then you are in a class and you are unable to understand what those real analysis terms and things are all about. First, let us understand why shall we study and what is the reason. Now, what I mean to say is that this is a question which some of the students ask, or it might be going in your mind, that taken everything granted, say for example, is real analysis at all required? I mean to say, we can just pass in real analysis, or we can just, bypass those things which we are talking in this video. Is it at all required? Now, my answer might demotivate you. To some extent, no, it is not required. I mean to say, you can do good things, you can do anything without real analysis. I mean to say, you really don't need to prove the axiom, you can still make things go. But my point is that you won't be able to make out great things. You won't be able to really see the beauty of mathematics until you go to the roots. So every step and every formula that we go through calculus, there are some results which are taken for granted, and these results, how we are proving. Sorry, you can take an algorithm of building a house. So we actually build the edifice, and we understand what are the proofs behind those theorems, and then we understand basically the roots. So, so what I'm trying to tell is that why should we start study on real analysis? My answer would be to enjoy the beauty of mathematics, one. Second, to understand really your roots. I can say you can understand who your great grandfather or great great grandfather or grandmother was. So it would basically give you understanding of the roots. You will really enjoy, and you start enjoying the basic understanding of mathematics. So why should we study reanalysis? So here on your screen, what you can say is this. So you can just go through that. So why do we need to understand real analysis? So right on your screen, I have given a kind of an idea. So now, this is the reason you should understand real analysis. What I would appeal to all my dear viewers and all my dear students is that you might have a question that, okay, without real analysis, things can go, things can glide, even things can drop. But The problem the students or other people, those who are graduating as math major, faces that reanalysis often comes as a very boring subject. Why boring subject? Because it deals with certain abstractness which the mind is not prepared or the brain is not wired towards these abstractness. Why this is abstract? Because we are not directly dealing with formulas which we can just plug in and things starts to happen, but we are going to find out why a multiplied by b equals to b multiplied by a. So we are really going back to the root. So this is a kind of an overview that why you should go real analysis. It is building like a house, building an edifice, and then based on that edifice you build further structures. So it gives you a complete understanding, and most importantly, enjoy the beauty of mathematics. Okay, so here comes the central part of the video, that what are the topics of reanalysis. Now, I would like to tell you that why I am showing you the topics, there is a specific reason. I will explain you further. So first of all, here on your screen, these are the general topics of real analysis. So we deal with limits, sequence and series, we deal with convergence, functions, derivatives, integral, fundamental theorems, etc. Right? So in fundamental theorem, so you can see that we have L'Hopital's rule, we have Taylor's rule, we have mean value, we have Bolzano-Weierstrass theorem, right? So, for example, if you take the mean value theorem, we already know that for a given planar arc between two endpoints, there is at least one point at which the tangent to the arc is parallel to the second. I'm just giving you a basic idea of the mean value. We know what is a L'Hopital's rule, a theorem which provides a technique to evaluate limits of intermediate forms. And we have Taylor's theorem and so on. So this is basically an idea that these are the general topics. We won't go into these topics and deal with mathematics in this video, but there is a reason I'm showing you all those topics and what are the general fundamental theorems. There are many other fundamental theorems, but the general fundamental theorem. Now, apart from this, there are also several other topics. I mean to say, in the field of analysis, there are several other topics. Here on your screen, you get that. So you can also deal with asymptotic analysis, which deals with limiting behavior. You can also deal with convex analysis, which deals with convex functions and sets. You can deal with harmonic analysis, which is deals with functions as superpositions of basic waves. You can also deal with Fourier analysis and Fourier transform, one of the most common thing. You can deal with complex analysis, which extends the real analysis from real numbers and goes to complex number. The functional analysis, which deals with study of vector spaces with limit-related structures, and the non-standard analysis that deals with study using rigorous treatment of infinite symbols, right? So these are the topics which is generally covered. All the textbooks, all the good books do have topics. But my basic intention of showing you this topic is that we won't go forward with this topic or this sequence. I have often seen that students get confused when they are, looking over the book and they're finding, oh my goodness, there's so many topics. So shall we start with limit? Shall we start with integrals? The reason behind this is that let us understand that real analysis, we have to mentally come out of the realm of calculus. It is no more calculus, my dear students. It is absolutely no more calculus. It is a hardcore, proof-based, I would say, much more rigorous math class. So, when you see this kind of a sequence which deals with so many topics, etc., don't get confused. These sequence or these topics would be covered in a different way, which is I'm going to show you in the next part. And if you follow this sequence, the conceptualization of those topics will become easier. It will create life more easier. And sequentially, if you go through that, that will give you a better understanding of real analysis. So let us come out of the realm that we are not studying calculus. We are extending calculus in a much more rigorous, proof-based mathematical model. And that is what I'm going to show you how you are going to study the topics so that it becomes easier for you. So, given those topics which I showed in the previous part, this section deals with how to study real analysis. Now, when I say how to study real analysis, I'm not going to show you problems, mathematicals, that will be a second part of the video. But what I'm going to show you that how sequentially you can follow. Let us start with this sequence so that things become better. First, write on your screen the real number system. Now, the calculus in general depends on the properties of the real number system. So, first of all, to get a foundation, we first understand how to develop real number from the base. So, we are dealing with real numbers. Obviously, that is why it is called real analysis. So, the first real number system, number one in your sequence of study, would be to develop a kind of a real number system from the base. So, the system of real numbers are there which satisfies the axioms. So present a set of axioms that form a logical base. So the closure property, the commutative law, the associative law, the finite and the infinite, the open interval, the closed interval, the system of induction, all these starts right at the base. Now I just told you that knowledge is like a pyramid. So you can understand that we are now forming the base, that is the real number system. So once we form the base, which will be a little bit a longer one because knowledge is like a pyramid. So first topic would be understanding the real number system and understanding those laws, closure, commutative, distributive law, and how these laws are being proved. Because until we now you see in calculus what we used to do, this associative, finite, infinite, all these rules are given to you, right? You just plug in the rule and you solve the mathematical problem. We are going a step back, a further step back, in order to understand that how these rules came from and can we prove this system. So we are getting to the base of the pyramid, which is why the base is a little bit longer, and that is why things are a little bit broader, and as we move up the tip becomes slower. So first we are done with what is called establishing a real number system. Very important. Don't skip the first concept, otherwise further the pyramid will collapse. Right. Number two, continuity and limit. Right on your screen. So as you see that calculus deals with functions and formulas and derivatives, most important is that we spend a lot of time, right, calculating those derivatives back to our school or our college days. But you must note also one thing, that all functions do not have derivatives. For example, this one, also this one, and this one, they do not have derivatives even at x equals to 0. You can later calculate it. So what we are doing is that in the continuity and limit section, what we are doing is that we are extending the basic properties that we started, which was without proof. So here we provide the proofs on the theorems. So limits at infinity, limits of sequences, these are now being proved, which was otherwise taken care as direct formulas. So first we dealt with the axiom part, then we start with the continuity and limit part, and we find that how these are proved and these are extended. Okay, so far so good. The third thing which will come sequentially is this one right on your screen, the basic properties of functions on R1, right? So in calculus, we have continuous function, right? So we have a lot of continuous functions. So here we use the IVT, which is called intermediate value theorem. When we have 2 points, then there will be at least one place when the curve crosses the line. We all know this IVT. Further extension of IVT, can we prove that? Also, we will deal with something which is called upper bound, the great infimum supremum, you all know, greatest lower bound, the Bolzano-Weierstrass theorem, and the uniform continuity. Again, please try to understand that we are not dealing with formulas anymore. We are dealing with the proofs of those formulas, how things are coming through. You might get a little bit bored why I'm repeating and repeating, but this is required so that it gets wired in your brain. So the basic properties of functions on R1 or those functions, those formulas, IVT, upper bounds, etc., right, which we come one by one and we deal with those proof. I hope you are now started to enjoy what is real analysis. Fourth part, which is elementary theorem of differential, right on your screen. Now, what would I say? In calculus, we deal with a lot of theorems, a lot of formulas of differentiation, right? But these are all without proof. I would say they really don't have any proofs. We just get those formulas and we plug into that. So now here, if you can see, this is what I'm trying to show you is basically a usual formula of derivative. We all know this one, right? Now, the most important part is that once we go for the fourth chapter, which is elementary theory of differentiation, what you will notice is that this particular derivative will have 7 further implications. It will have 7 further theorems which can be deduced from a simple derivative. That is the beauty of real analysis. So here what we do is that we establish the chain rule. We have solved papers after papers solving formulas and chain rule, but here what we do is that we solve the chain rule. We establish the chain rule by rigorous proof. We also find out mean value theorem, the Rolle's theorem, and the L'Hopital's rule. All of these are no more rules, but we are proving one by one, step by step, so that we can prove those rules. So the L'Hopital's rules, the Rolle's theorem, the mean value theorem, all we have used it, but without knowing that where from they emerged, who gave their birth. So this is one. Okay. So 1, 2, 3, 4, 5. Let me quickly go back. I hope this is not a too long kind of a session. So first we established the real number system, which is giving you the base. Then we started with continuity and limit, and we went forward and saw that certain functions don't have derivatives, and we are extending them. Then we dealt with basic properties of functions on R1, the upper bound, greatest lower bound, etc. Then we started with the elementary theory of differentiation, which we already know, and now we are coming to the rules. Okay. We all know about integrals. Here, right on your screen, this is called the elementary theory of integration, where this chapter basically deals with proving those theorems. What are those? It is our Darboux integral, fundamental theorem of calculus, we all know in the first form, fundamental theory of calculus in the second form, the Riemann integral, and we all know logarithmic and exponential functions, but here we deal with defining and developing logarithmic and exponential functions. So we started with that one. We started the base, and then there is an integration, elementary theory of integration. Then we start with the elementary theory of, the differentiation, and then with the integration part. So all these fundamental theorems, the Darboux integrals, the Riemann integral, which we have been using throughout, are now being established, and you can really see the birth happening. The real birth of calculus is happening here. Coming to the sixth part, which is called this one, elementary theory of metric spaces. So now what I would like to tell you that till now we have been developing properties or functions from R1 to R1. Now we need to prove theorems of two more variables. How we do that? So we develop a kind of a rule, a function in one metric space, and then we extend that to any other metric space. So you can call that Euclidean space to n-dimensional space. Here we call it functions in one metric space, which is getting generated or generalized into another metric space. What are the topics that we deal about? So we deal about Schwarz inequality, we deal about triangle inequality, we deal with topology in metric spaces, and we deal with countable and uncountable sets. So this is the, again, now we have known the integration and the differentiation and the basic properties of functions on R1. Now we started developing the theory of metric spaces. Why metric spaces? Because now we really want to take forward the Euclidean rule or the Euclidean spaces further to n-dimensional spaces. Okay. Here on your screen, this is the seventh topic, which should come chronologically so that there is no confusion. It is called differentiation and integration in Rn. So now you see that we are further extending it to n-dimensional. So this is basically generalization of the ordinary differential equation and partial differential equation from Rn to R1. So more or less the topics which we cover in this particular are the partial derivatives in Rn, number one. We covered the Taylor's theorem from Rn to R1. We covered the Darboux integration in Rn, and we covered the Riemann integration in Rn. So this is quite self-evident. I don't need to say you further that what we are dealing with. So the seventh one comes with differentiation integration. Once the rules are established, once the metric spaces is established, now we move ahead with Rn. Okay. The next part I won't take more time because it will take more technical stuffs to to explain. This is one which is called test for convergence and divergence. We will come to that part later when we start with mathematics. The ninth part or the next part in this series sequentially which is coming is Riemann-Stieltjes integral, and this actually is nothing but the generalization of the Riemannian integral. So we all dealt with Riemannian integral in calculus. Now we are generalizing it. So you see step by step how things are proceeding, step by step how things are increasing and getting generalized. The next one is this, the implicit function theorem. It allows relations to be converted to function of several real variables. So it gets into several real variables. That is why it is called the implicit function theorem. The last part, which is in our sequence, which comes, is this, vector functions in Rn. Now, what happens is this, in this section, we try to set coordinate-free definition. So you might be recalling from my previous video when we talked about differential geometry. If you go to my playlist in differential geometry, we have been talking about differential geometry. There was a series of talk on differential geometry. You will see that on differential geometry also the basic purpose is to free ourselves from a set of coordinates and move into coordinate-free transformation, coordinate-free geometry. Vector functions in Rn, this chapter also deals with set of coordinates for coordinate-free geometry. So what are the areas that we are covering? We are covering vector functions extending to Rn. We are covering Green's theorem in R2. We are covering line integral in Rn. And we are covering the Stokes theorem and the divergence theorem. Okay, so more or less what I would say that this is how the sequence should go. So we first establish the real line, the base, then we understand the continuity and limit, that there are certain derivatives, not all functions do not have derivatives, and how we can prove into limits at infinity and limits of sequences. Then what are the basic properties in R1? And these deals with intermediate value theorem, upper bound, lower bound, all those things, and how we can extend that. Then comes the elementary theorem of differentiation, where we establish the rules of differentiation. We see the birth of chain rule, the usual derivative, the Rolle's theorem. All these are now proved. These are now hardly proved, clearly proved. Then we come to the elementary theory of integration, where we come to know about the integrals, Darboux integral, fundamental theorem in first form, second form, etc. Then we start developing metric spaces, where Schwarz inequality and triangle inequality are being proved. Then we deal with differentiation and integration in Rn, where this Taylor's theorem, etc. Convergence, divergence, Riemann-Stieltjes integration, which is an extension of the Riemannian integral, the implicit function theorem, and the vector functions in Rn. The basic target of this one is to set a coordinate-free definition, and it covers line integral in Rn, Stokes and divergence theorem. Well, what I would like to do right now is I would like to take a pause of this video. The reason is that the video would unnecessarily get longer. So what I will do is that I will make a pause of that video, and what I would like to tell you is that we dealt with the introduction part. We understood really what real analysis is all about, how it is a hardcore proof-based mathematical model, how the transitivity, the commutative and distributive law are being established. So we say it is a rigorous proof-based definition of real number axiomatically. Now you see why I call it defining real number axiomatically right at the beginning. So when you go through the topic part, you see at right at the base of the pyramid, I told that how we can define real number axiomatically. Also, we define the entire process of real analysis in steps: defining real number, setting down the properties, building the number system, from that the foundation, and finally extending from Euclidean to n dimension or with several variables. We also dealt with real analysis. Yes, it is very much helpful for data science. I give you a brief understanding how real analysis is important. Why should we understand real analysis? Very important. Until that, we don't get the motivation. The overall topics of real analysis, and one by one, what those topics dealt with. And this sequence, if you follow, I think that it would be good for you, instead of going and jumping into any kind of a topic which your book has. Right. So we take a pause of this video, and in the next video, what I'm going to do is that I'm going to define certain areas about the prerequisites of real analysis. Is real analysis at all difficult? And a very important surprise. The surprise would be, well, I won't say what would be the surprise. So watch out for the next video. Do subscribe, like, and comment, because I will be waiting that for this kind of a demanding subject, how my video has really helped you. Put on your comments, write to me at editor@physicsforstudents.com. Until that next time, when we come across with more interesting subjects, and it is going to extend this video better, because I'm going to give you a lot of tips, techniques, so that you can really, boom, you can really amaze your professor that you're doing great in real analysis. Bye, up till then, stay safe and stay happy, and have a nice understanding of real analysis. Bye bye.